Okay, colligative properties. Have you ever made ice cream at home? Yeah. So you can't just use plain ice. You have to put salt on the ice. If you haven't made ice cream, have you ever tried to take ice cream or ice cream bars or popsicles like to a picnic in a cooler? It's not a good idea. You can pack them with ice. They're covered in ice, and you go to eat them, and they're all soft and melting. What's up with that? Salt is added to the ice in an ice cream maker, and we'll be doing that in lab next week, because it lowers the temperature of the ice. It's really kind of crazy. Ice freezes at, well, ice melts, water freezes, whatever, right, at 0 degrees Celsius. If you throw salt in there, the temperature at which that freezes goes down to minus 10 degrees Celsius. And we're going to talk about why that is and how that works. But this is called freezing point depression because it depresses the freezing point. This is called a colligative property. And colligative properties are properties that depend on the number of particles dissolved in a solution. They do not depend on what those particles are. So they're kind of weird that way. You'll get this freezing point depression whether you use potassium chloride or sodium chloride. It's the number of particles. Stupid train. So the one thing that is a little different is if you're dealing with electrolytes or non-electrolytes. And the reason for that is when you dissolve an electrolyte in water, it separates into ions and it makes more particles, right? You put 1 mole of sodium chloride into water and dissolve it, and you get 1 mole of sodium ions and 1 mole of chloride ions, right? So you get 2 moles of particles. If you put a mole of sugar in water, you get 1 mole of particles. So electrolytes have a bigger effect because they make more particles. Let's look at vapor pressure lowering. So if we've studied vapor pressure, here we have a liquid, let's call it water, in dynamic equilibrium. In this closed container, we have evaporation, we have condensation, we have a vapor pressure here because some of this water is in the gas state, and that exerts a pressure. If we throw something else in there, a solute, so now we've thrown these red things in, that does not affect the rate of condensation because the rate of condensation depends on how many gas molecules are bumping around up here and how fast they run into the surface. But it does affect the rate of evaporation because in order for the water to evaporate, it has to get to the surface, right? And now there are these solute particles that are in the way. They're blocking. It's like, you're trying to drive down a road and there's all these cones and barriers and stuff, and you keep having to slow down and get around them, and it slows traffic, right? So when you put a solute in here, it slows down the rate of evaporation. Well, the rate of condensation depends only on how many particles are up here, and so the rate of condensation is eventually going to slow down because the rate of evaporation is slower and we've got fewer particles up there. So fewer particles up here means lower vapor pressure. Does that make sense? So that's one explanation. Another explanation has to do with entropy, that nature's tendency towards mixing, of spreading energy. And this is a really crazy experiment. So here we have like a cake plate, and we've got 2 beakers in here. One has pure water, and one maybe has salt water in it. And you put the lid on it, and you leave it alone. It does take a long time to do this. You leave it alone, you come back, and what you'll find, bless you, is that the level of the water, the pure water, is lower, and the level of the saltwater solution is higher. So how do water molecules get from one beaker to the other? It's not magic. They evaporate. They evaporate, and then they condense over here. It seems like magic, and it's not sleight of hand or anything. It just does it all by itself. But you've got these two solutions, and you have evaporation occurring, and you have condensation occurring. So both of them begin to evaporate, and you get a vapor pressure inside this container. The rate of evaporation on this one is lower because it is got the solute in it. But once we get an equilibrium going here, then the rate of condensation is the same for both of them. And so we have this net effect of more water molecules depositing or condensing into this beaker than in that beaker. The effect is the same thing as the osmosis we talked about at the beginning with drinking seawater. Or putting, having that aquarium with the divider, and you've got salt water and fresh water. And you take away the barrier and it mixes, right? This is mixing, but it's not even in direct contact. Nature has this tendency towards mixing. Any questions or comments on that? That is crazy, right? This doesn't seem possible.
So is it considered closed system?
This would be a closed system, yeah, because the water molecules cannot escape from this cake plate. They can escape from one beaker, though, and end up in the other beaker, and they will. So if you want to think about it in less scientific terms, I think of, well, nature's trying to make everything the same. It's trying to level everything. This is less concentrated, doesn't have any solute. This has some salt in it. It's trying to make those solutions the same. So it's putting more water into here, and there's less over here. So this is becoming lower and lower in concentration. So, you know, sometimes the cute personifying atoms as people thing is what you can remember, right? And so whatever helps you remember is fine with me. Of course, we can quantitate this. This is quantitated using Raoult's law, which says that the partial pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So P solution, vapor pressure of the solution with the solute in it, and the mole fraction of just the solvent by itself, and the vapor pressure of the solvent when it's pure. And that has to be at the same temperature as this P solution we're measuring. So if we think about this, if we had a pure solution, pure solvent, what would chi for the solvent be, the mole fraction? If there was no solute, it'd be 1. Mole fraction is the moles of solute divided by, wait a minute. This is not moles of solute, this is moles of solvent. Yeah, okay, because that was not going to work out well. It'd be undefined. The moles of solvent divided by the moles of solution in total. Well, if there's no solute, then they're the same, and this number is 1. And then 1 times the vapor pressure of the pure solvent is just the vapor pressure of the pure solvent, and so we end up with the vapor pressure of the pure solvent being equal to the vapor pressure of the pure solvent. The vapor pressure of a solution is directly proportional to how much solvent there is. So the larger the mole fraction, the larger the vapor pressure. Vapor pressure lowering is the colligative property. And so this is looking at how much does the vapor pressure change. And I think your book goes through the mathematical steps from here to here I didn't put them in the PowerPoint because most of my students don't care. The change in the vapor pressure equals the mole fraction of the solute times the vapor pressure of the pure solvent. Okay, so using these equations isn't that hard. It's trying to remember them. So I'll give those to you. Let's do an example. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees is 23.8 torr. So we want the vapor pressure of a solution. So we need to use Raoult's law. So the vapor pressure of the solution is equal to the mole fraction of the solvent. What's the solvent here? Water. Times the vapor pressure of the pure solvent. Well, do we know either of those?
Vapor pressure of pure water.
Yeah, we know the vapor pressure of pure water. They told it to us. It's 23.8 torr. We're trying to calculate the vapor pressure of the solution. So we need to find the mole fraction of water. So the mole fraction of the solvent. Calculating the mole fraction comes out very similar whether you're looking at a solute or the solvent. Mole fraction of H2O is the moles of H2O divided by the total number of moles in the solution. So that's the moles of water plus the moles of, I'm going to call ethylene glycol EG, because I don't want to write all that out. Well, how do we find the moles of water? What did they give us? They gave us mass of water, right? Well, we can change a mass into moles. So we've got 285.2 grams of water. I'm going to use the molar mass, grams on the bottom, moles on the top. 1 mole of water weighs 18.02 grams, and the grams cancel. So 285.2 divided by 18.02. This should have 4 sig figs, so we want to keep at least 4. Excuse me. And then we're not done yet, so I'm going to keep 2 extras. So that's the moles of water. So I can put that in here, 15.8269. And then in the denominator it shows up as well. And we have to add in the moles of ethylene glycol. Similar process, different molar mass, right? We've got the mass of ethylene glycol. So we're going to multiply by moles, divide by grams, and we need a molar mass. So we got 2 carbons there, 2 times 12.01. We got 2 oxygens, so plus 2 times 16. And there's 2, 4, 6 hydrogens, 6 times 1.008. I'm getting 62. Anybody else get that? Okay. 62.068. Oops, 6 disappeared. So 55.3 divided by 62.068 equals 0.89. The mass had 3 sig figs, so this result needs 3 sig figs, carry 2 extras, and 6 moles of ethylene glycol. So we put that down here. And then we do the math, 15.8269 divided by, open parentheses, 15.8269 plus 0.89096, close the parentheses, equals, whoops, 0.946706. You can't cancel the 15.8 with 15.8 because there's adding in the denominator. The moles cancel out though, because you have moles plus moles. So you have moles on the top, moles on the bottom, the units go away. Is this a reasonable mole fraction? Yeah. Mole fractions should be 1 or less. If you get more than 1, you have a problem with your math or something. So this is our mole fraction. So that's what we need to put in here for chi H2O. 0.946706. And then we're given the vapor pressure of pure water at the same temperature, 23.8 torr. Multiply, and I'm getting 22 point, this should have 3 sig figs because of this vapor pressure, so I'm going to go ahead and round it here, 22.5. The unit is torr. Any questions?
So it's going to be in torr. You can do it in atmospheres, or
You could do it in atmospheres. The unit here comes in torr because we had the vapor pressure, the pure solvent, in torr. So whatever unit this is in is what your final pressure will be in, because the mole fraction is unitless. This is a reasonable number because adding a solute causes the vapor pressure to go down. And this number is smaller than that, so that's a good sign that we did it correctly. Any other questions? So there are some complicating factors with this vapor pressure lowering. If the solute is volatile, do you remember what volatile means? Evaporates easily. If it is volatile, it's going to contribute to the vapor pressure of the solution. If we've got salt and water, salt doesn't evaporate to any significant degree at all. So the only vapor pressure is from the water. But if we have like acetone and water mixed together, acetone is a volatile liquid and it'll evaporate as well. And so we get more than one gas as our vapor pressure. So when we talk about an ideal solution, that's a solution that behaves in a very nice, predictable way. It's going to follow Raoult's law at all concentrations for both the solute and the volatile solvent. So the total pressure above an ideal solution is the sum of the partial pressures from each of the components. So there'll be a vapor pressure from the solvent, there'll be a vapor pressure from the solute, you just add them together and you get the total pressure. Non-ideal solutions don't follow Raoult's law. And this is because of interactions between the solute and solvent particles. If those interactions are stronger or weaker than the interactions between the solvent molecules, then the vapor pressure that you calculate from Raoult's law is going to be off, either higher or lower. So in panel A, we see a graph for an ideal solution. What we're looking at is an increase of vapor pressure on the y-axis and looking at increasing the the mole fraction of component A on the x-axis, going from 0, no solute, up to all solute. And you say, well, how could you have all solute? Well, with many solutions you can't. But if you have two liquids that are miscible, like alcohol and water. Miscible means that they will mix and form a homogeneous solution in any proportion. You could have a drop of ethanol in a glass of water. It'll mix up just fine. You can put a drop of water in a glass of ethanol, and it will mix just fine. That's not true of all liquids, even those that are soluble. But for those that are, you can go in a mole fraction going all the way from 0 to 1. In an ideal solution, each of these components behaves as if it were the only component. So as we increase the mole fraction of A, we see that its vapor pressure increases. If we're increasing the mole fraction of A, that means the mole fraction of B is going down. And so the vapor pressure of B starts high and goes down to 0. The total vapor pressure is the sum of both of them, and it's this purple line right here, because red and blue make purple, I guess. Any questions about that? Does that make sense? Panel B, we've got strong solute-solvent interactions. So the solute and the solvent are really digging each other, and they're like, hey, we like hanging out here. That's going to cause the rate of evaporation for both of them to go down, because they're going to kind of hang on to each other. So here we see for A, as its mole fraction increases, this dotted line is what we expect. I'm not pointing to the dotted line. That dotted line is what we expect from Raoult's law. What we actually observe is the red line, and it's less than what's expected. And the same for the component B. What we observe is that the vapor pressure of that component is less, because the solvent and the solute are hanging out, they're attracted to each other. And so they don't evaporate as much. And when we add those two bowed lines together, instead of getting the straight line up here, we get a curve with a big dip in it. Okay, so the vapor pressure is significantly lower than what you would expect. Questions? If we have weak solute-solvent interactions, they're weaker than the interactions between the solvent molecules themselves. So here, these people, in my mind, they are people. The solute and the solvent don't like each other. It's not just that they're neutral to each other, they're like actively not liking each other. And so they're trying to get away from each other. And that will cause the rate of evaporation to be greater, and so the vapor pressure is higher than expected, because they're trying to get away from each other. It'll do that for both, and so then the vapor pressure of the solution has this hump in it. It's higher than expected. Any questions? I'm not sure if that sunk in, but nobody's saying anything, so we'll go on. Just need a minute.
So strong solute-solvent interactions would be more of a, it would be like an ionic, something ionic solute that's been dissolved in it? Or?
Well, you're on the right track, except that ionic compounds are not volatile.
Oh.
But if we think of, say, ethanol and water both have hydrogen bonding as their strongest intermolecular force. And so they're going to like each other a lot. And so I would expect that because of that strong interactions between ethanol, the solute, and water, the solvent, that the vapor pressure would be lower than we expect. If you have something that's maybe polar but not, doesn't have hydrogen bonding, you may begin to see this behavior where the solutes and the water, they're just like, trying to get away from you. It's not so much that they won't mix, but they're not really attracted to each other. You could think of it this way. So if you've got maybe a solute with dipole forces, but not hydrogen bonding, and you're looking at water that has hydrogen bonding, the water molecules are so attracted to each other that they're kind of squeezing out the solute molecules. They let them in enough that we made a solution, but they're just not feeling very welcome. And so they're going to be more apt to leave the solution than if they really felt engaged and welcomed into this solution. I know, it's getting a little off. Does that make sense? A little bit. Well, that's good enough for now. Okay, so we're going to do some calculations. A solution of benzene and toluene is 25% benzene by mass. At 25 degrees Celsius, the vapor pressure of pure benzene and pure toluene are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following. We will not ask you to do any calculations where it's non-ideal behavior, because the degree of non-ideal behavior depends on the specific solution. Okay, for that we more want you to be able to say, well, would it be higher or lower? So here we're going to do a calculation with ideal behavior, and they're wanting us to find the vapor pressure of each of the solution components in the mixture. So what's the vapor pressure of toluene? What's the vapor pressure of benzene? Well, how do you find the vapor pressure of the solution? Raoult's law. So the vapor pressure of, we'll call them T and B. So the vapor pressure of toluene is going to equal the mole fraction of toluene times the vapor pressure of toluene by itself. Now, let's think about that. The total pressure for the volatile solvent is pressure A times pressure B. It's the vapor pressure of each of them. In this, when we first started talking about it, we were assuming that the solute was not volatile, just the solvent was. And so when we look at the pressure of the solution, it's all solvent. So I think my equation is okay. I just was second guessing myself. So let's go back here. So, and we'll just start with toluene. So to find the vapor pressure of the toluene, we need to find the mole fraction of toluene and the vapor pressure of toluene by itself. Well, that was given to us, right? Toluene was the second one, so this is the vapor pressure of toluene. 28.4 torr. So to do mole fraction, we need moles of toluene and moles of benzene, right? But they didn't give us masses or anything, they just gave us this percentage. 25% benzene by mass. Okay, so 25, well, it's 25.0. Let's be careful. 25% benzene by mass. What does that mean? 25% of whatever you want, but another way to do it is 25 grams per 100 grams, right? So we could express this as 25.0 grams of benzene per 100 grams. Well, that's going to be an exact 100. 100 grams of solution. What's in the solution? Benzene and toluene. So the mass of benzene plus the mass of toluene has to equal 100. Make sense? We know that the benzene is 25 grams. What's the mass of the toluene then? 75. So we could replace this with 25 grams of benzene plus 75 grams of toluene. Does that make sense? That looks like something we could maybe turn into a mole fraction, at least a mole fraction for benzene, right? Here we have grams of benzene on the top, and we have grams of benzene and grams of toluene. We can change grams into moles, right? So if that's the percent of benzene, what would the percent toluene be? 75, right? There's only two things in this solution. So the toluene is 75%. So 75.0 grams of toluene divided by 25 grams of benzene plus 75 grams of toluene. So not the only way to get at this problem, it's what is coming to my head right now. So we need some molar masses, don't we? We need a molar mass of benzene and one of toluene. So benzene, 6 times 12.01 plus 6 times, that's not a 6, 6 times 1.008. So I'm going to write those up here, 78.108 grams per mole. That's for benzene. And toluene is 7 times 12.01 plus 8 times 1.008, 92.134. Okay? So we've got 25 grams of benzene, we've got 75 grams of toluene. So let's find out what those things are. Where am I going to do this? I'll do it right here. I'm going to change to a different color so it doesn't look like I'm continuing on. Let's take 25.0 grams of benzene. We're going to use the molar mass of benzene, 78.108 grams per mole. So 25 divided by 78.108. 0.32007 moles of benzene. I do the same thing for the toluene. 75.0 grams of toluene times its molar mass, 92.134 grams. .81403 moles of toluene. We have moles of benzene, moles of toluene. Now we can calculate the mole fraction for toluene. I'm going to make a little space up here. Mole fraction of toluene equals moles of toluene divided by moles of toluene plus moles of benzene. So we're going to use those numbers we just calculated. 0.81403 divided by moles of toluene. Someone's having too much fun in the next room. Why aren't we laughing? I know why we're not laughing. So, any questions about what I'm doing up there? So I've got 0.81403 divided by, open parentheses, 0.81403 plus 0.32007, close parentheses, equals 0.717. That's going to end up with 3 sig figs. And there's a whole bunch of 7s after that. I'm going to keep 2 extras. And that's a unitless quantity. This is the mole fraction of toluene. So this is where, especially like on an exam, you're like, oh, I got this answer. Why was I getting that answer? Do you ever find yourself thinking that? I did this calculation, but I can't remember why I started it. This is the mole fraction we needed to plug in over here. The mole fraction of toluene, and then we've got the vapor pressure of toluene by itself, 28.4 torr. So this is 20.385. I'm not going to round that. I kind of think there's more parts and I might have to use that again. But the answer for the vapor pressure of toluene in the mixture would be 20.4 torr.
What is the solvent in this one?
That's a good question. What's the solvent? So we've got 2 liquids. It's the one that there's more of. So it's 25% benzene and 75% toluene. So toluene would be considered the solvent.
Is there ever a case where the smaller one is ever the solvent? Or is that just
Yes, of course there's cases where the smaller one is the solvent. Because there's like exceptions to everything, right?
So,
We're gonna pretend it doesn't happen.
so are you supposed to use the mole fraction of the solvent instead of the...
Okay, that's a good question, and that's why I kind of had a brain fart and went back and looked at the original Raoult's law. So when we said that it was the pressure of the solution equals the mole fraction of solvent times the vapor pressure of the pure solvent, that is assuming that the solvent is the only thing evaporating. That would be true for a solution like sodium chloride in water. The sodium chloride is not going to contribute any vapor pressure because it doesn't really have a vapor pressure. Putting it in there will mess up the evaporation of the water, and so it'll lower the vapor pressure, but it's not going to contribute. This is a situation where we have a volatile solvent and, a volatile solution, a volatile solute, and the solution is also evaporating. So here, whether we're looking at the solute or the solvent, it doesn't really matter. They're both giving a vapor pressure. Does that make sense? And so the vapor pressure in the mixture is proportional to the mole fraction of that. The more moles of this, the closer the vapor pressure of this from the solution will be to it when it's pure. So that's one answer. We also need the vapor pressure of the benzene. Do we have to do all of this over again? No. We could, but we don't have to. If this is the mole fraction of toluene and there's only 2 things in the solution, what's the mole fraction of benzene? 1 minus that. So the mole fraction for benzene, chi B, is exactly 1 minus the mole fraction of the toluene. It's like percentages have to add up to 100. Mole fractions are just percentages divided by 100. They have to add up to 1. So 1 minus 71778 is 0.28222. So that's the mole fraction of benzene. So we can take the mole fraction of benzene like this and multiply by the vapor pressure of pure benzene and get the partial pressure, the vapor pressure from the benzene. And that was 94.2 torr. So that equals 26.585 torr, 26.6 torr. So that's for the benzene, and this is for the toluene. Any questions? Question B, what's the total pressure above the solution? Well, we calculated the pressure of each, and we're told to assume ideal behavior. So the pressure of the solution as a whole, the vapor pressure total, is going to equal the pressure of toluene plus the pressure of benzene. The benzene was 26.585 torr. And the toluene was 20.385 torr. So we add those together. Having trouble with the calculator. 20.385 plus 26.585. Calculator says 46.97 torr. Sig figs with adding should stop there, so that rounds to 47.0 torr. Any questions? Oh yeah, part C. Dang. Okay, the composition of the vapor in mass percent. Right? This one's a little bit hairy. Okay, so we've got, let's review what we've got here. We've got the partial pressure of toluene was 20.385 torr, and the partial pressure of benzene was 26.585 torr. Did I get that right? What do we know about the partial pressures of gases in a mixture? Each gas behaves like it's the only one, right? And the pressure of a gas is proportional to the number of molecules, right? Could we calculate from this pressure how many molecules there were above this liquid, and then the mass of it. We could. We don't know the volume, we don't know the temperature. We just got the pressure and we want N. So what could we do with that? Well, we also looked at mole fractions with gas mixtures. Do you remember that?
So can you find a mole fraction of each gas and then?
We could find a mole fraction and convert that to a mass percent, like we took the mass percent and converted to a mole fraction. We could do that. So the partial pressure of an individual component, let's do toluene, is equal to the mole fraction of the toluene times the total pressure of the gas mixture. If you go looking back in whatever chapter that was, I think it was chapter 5, you'll find that. The partial pressure of a gas in a mixture equals the mole fraction times the total pressure. So we have the total pressure and we have the partial pressure of toluene, and so we can calculate the mole fraction. You could also take this, just make up a volume and a temperature, calculate the moles of each in this imagined volume at this imagined temperature, and you could do it that way and that would work. But it's going to take more steps. So our total, again, pressure total, capital T, 46.97 torr. So the mole fraction of toluene is going to equal the partial pressure of toluene divided by the total pressure. So it's 20.385 torr divided by the total pressure, 46.97 torr. Torrs cancel out. 20.385 divided by 46.97. Mole fraction is 0.434. Those guys had 3 sig figs. 0, 0. That's the mole fraction. So that is equal to the moles of toluene divided by the moles of toluene plus the moles of benzene, right? So this mole fraction, we could write this as that number over 1, right? If this number over 1 is equal to this, and NT, that means NT is 0.434, and so down here, 0.434 plus something has to equal 1, and we can figure out the moles of benzene. So if the moles of toluene equals 0.434, it's not torr, that's moles, then the moles of benzene equal 1 minus 0. I'm having trouble today. .565. Wow, that's that's going to round up to 600. So we've got moles of toluene, moles of benzene. How do we find the mass percent? You have to convert these to masses, right? Let's get rid of the blue line too. Okay. We have 0.434. Wow. I guess you can kind of read that. That's grams of toluene. So we need the molar mass of toluene. To get the mass of toluene. This is for T. And for benzene, we've got 0.56600 grams times its molar mass. Oh, I don't know if I can go back far enough in my calculator. So benzene was 92.134. And toluene was 78.108. So grams cancel, we end up with moles. 0.434, oops, clear. 0.434 divided by 78.10. What did I do? You see what I did? I screwed up. I screwed this up. What did I do wrong? What unit do I have on these numbers down here? Moles. And up here I wrote grams. Because I spaced out, I guess. I don't know. So that's not going to work, is it? So let's try again. It's important to write units. I just stuck on that. Okay. It was 78 point what? Did anybody write it down? Nobody did. And I think
78.108.
Thank you, 108 grams per mole. Okay, 0.434. I'm having an argument with my calculator. Okay, 0.434 times 78.108. 33.898872. That's grams. Grams of toluene. And then this one, 92.134. And that's not grams. That's moles. Moles cancel. 0.566 times 92.134. Yeah, I need to print this. Missed some digits in there. 2 point. Okay. 52. Anybody get that? Seems reasonable. 52.148 grams of benzene. And we have to remind ourselves, what are we trying to find again? Mass percent. So mass percent is the mass of what we're looking at divided by the total mass. So the percent by mass for toluene will equal the mass of toluene, 38.899 grams of toluene, divided by the total mass, which is those two added together. 52.148 plus the 33.89. So that is 86.047. And then to make it a percentage, we multiply by 100%. So 33.899 divided by 86.047 equals times 100. 39.4% toluene. And we don't have to do another big calculation to find the percent of benzene. It's just 100 minus 39. Yeah, 60.6. So 60.6% benzene. Whew. Some people think calculations like that are fun. They are in the minority, and I find that fun, but I don't expect that all of you are going to enjoy that. So any questions about the calculation? There was a lot. Then there's this question at the bottom. Why is the composition of the vapor different from the composition of the solution? Why isn't it the same? Any ideas? Their evaporation rates are different. The vapor pressure of the pure substances is not the same. Which one's more volatile? No. Oh, yeah, benzene. Sorry, that's the first one. I was looking at toluene and this. So the benzene is more volatile than the toluene because it has a higher vapor pressure. And so what we see is the original solution was 25% benzene. In the vapor, it's 60% benzene because the benzene evaporates faster than the toluene does. In the liquid solution, it was 25% benzene. In the vapor above, it's 60% benzene because the benzene evaporates more quickly than the toluene. So it contributes more to that vapor pressure.